Okay, so right now we are going to talk about solutions and concentrations. So as a consumer, you use many products that are sold in the form of a solute dissolved in a solvent, or a solution. Beverages, medicines, household cleaners, and hair products are all examples of commercial solutions that people use on a regular basis. In each case, manufacturers make sure that the ratio of solvent and solute are safe to use in an appropriate application. Changing this ratio can dramatically change the properties of the solution. So for example here, did you know that a concentration solution of acetic acid would hurt you if you drank it? Yet most people commonly use vinegar, which is a solution of 5% acetic acid, as an ingredient in their cooking. To keep consumers safe, there are regulations about the proper labeling of products, and the ratio of solute and solvent is often noted on this product label. So here we can see it shows 5% acetic acid. So in some cases, the solute may be a part of the product that is an unintended ingredient. Or PCBs are a pollutant that can be present in water. They may also be found in fish living in water polluted with PCBs. The maximum concentration allowed by Canada's health guidelines regarding the level of PCBs in fish that can be harvested to be eaten is 2 parts per million. This guideline is to ensure that the fish you eat will not harm you, and all of these examples relate to the amount of certain substances in the present solution. Whether it is the amount of PCBs in fish or the amount of acetic acid in vinegar, the ratio of solute to solution is described as a solution's concentration. A solution with more solute in it than solution of the same volume is said to be more concentrated, and a solution containing a large amount of solute per given volume is called a concentrated solution. A solution containing a small amount of solute per given volume is called a dilute solution. So there again, concentration is the ratio of the quantity of solution to a quantity of, concentration is the ratio of the quantity of solute to the quantity of solution, and a concentrated solution is a solution containing a high ratio of solute to solution, so meaning that it has a high amount of solute in that solution, and a diluted solution is a solution containing a low ratio of solute to solution. So concentrated solution and diluted solutions. So as we can see here, a concentrated solution has a high ratio of solute to solution, and a dilute solution has a low ratio of solute to solution. So the concept of concentration is something that you encounter every day, whether you are buying juice or cleaning products or looking for the government guidelines for water quality, you are dealing with concentrations. Understanding concentration will help you answer questions like the following. 1. How much of the solute is in the product you are buying? 2. What are safe and acceptable limits for certain chemicals in food or drinking water? 3. Are there safety concerns associated with products that have higher solute concentrations? Or 4. Can you save money by buying concentrated solutions and diluting them yourself? These are a few of the questions you will be exploring in this lesson and in the next. Not only will you find that understanding concentration gives you a greater knowledge of the information listed on the products you buy, but it will also give you a better understanding of how to interpret and analyze this information. So, quantities of properties of solutions. So you know the difference between concentrated juice and diluted juice because it can taste different. You should also be able to see a difference in color and consistency. You can get a lot of information about a substance simply by observing its physical properties, like color, taste, and odor. These are the qualitative properties of a solution. So as we can see here, this is the more concentrated solution, and this is the more dilute solution. And I'm using my sense of sight in order to be able to tell this. So qualitative properties of a solution is a basic attribute of a solution that you can observe with one or more of the 5 senses. So qualitative properties include a description of a solution's color, taste, transparency, color intensity, or odor. Caution: remember to never taste or inhale any solution prepared in a laboratory. So qualitative properties of solutions. Because a solute provides each solution with a new set of properties, qualitative tests can be used to detect the presence and, in some cases, identify the solute present in a solution. Often, the difference in qualitative observations between concentrated and dilute solutions is directly related to the number of particles of solute dissolved within the solution. The greater the number of particles in the solution, the greater the specific effect. Now, as we have seen this already, okay, with the concentrated solution having more dissolved particles, but it is not always easy, however, to use qualitative properties to compare the concentrations of solutions. This is especially the case for colorless solution. So how could you determine which of the following solutions has a higher concentration? It is impossible to tell because they are both clear. But as we explored earlier, one method to accomplish this task would be to compare the two different solutions' how they conduct electricity. It is possible to place two electrodes into a solution and measure how easily an electrical current can pass through the solution from one electrode to another. Solutions with higher concentrations are more effective than diluted solutions at passing the current through the solution. Qualitative characteristics of solutions. So all chemical reactions involve collisions between atoms, ions, and molecules. This idea is explained by collision reaction theory. This theory states that a chemical reaction will occur if the particles collide with a certain minimum energy and if they collide with a certain orientation. The rearrangement of particles that occurs after a collision is a chemical reaction. So collision reaction theory is a theory stating that chemical reactions involve the collision and rearrangement of particles, as shown here. The iodide ion comes in, reacts with this molecule. This molecule now contains the ion and is bringing out the bromine. So this reaction only occurs if the iodide ion collides with enough energy traveling from this particular direction. Okay, it would not occur if it happened in the other orientation. So a solution having a greater concentration of solute to solution reacts faster than a more diluted solution. This occurs for the following reasons. 1. A chemical reaction is a result of collisions between particles. 2. A concentrated solution has more particles of solute available for possible collisions than a dilute solution. And 3, the probability of a collisions increase as the number of solute particles within a system increases. So, the reactions with a concentrated solution occur more quickly because they have greater number of collisions, as we could see here. There will be a lot more collisions occurring than in this solution, where reactions with dilute solutions occur at a slower rate because the collisions are less probable. So there are 3 methods for communicating concentration. You can sometimes determine the relative concentration of solutions by observing their qualitative properties, but it is often very useful to know specifically how much solute is dissolved in a particular solvent. In science and technology, a variety of ways are used to communicate the concentration of a solution. So this table that we're about to see summarizes the 3 common ways to express concentration. The first one is percent by volume. Alright, the formula or the symbol here is percent and volume over volume, percent by volume. The formula is the milliliters of solute divided by the milliliters of solution times 100. Okay? Its use is communicating the volume of a liquid solute dissolved in the total volume of a solution, and it is generally used by manufacturers of consumer products. So we've seen this often on, we saw that on the vinegar with the acetic acid, had a percent by volume. You also see this on liquor, okay? So liquor is a very common place where we see a percentage. Parts per million, its symbol is ppm, okay? And we generally do a gram of solute divided by a gram of solution, and then this is times by a million, or times 10 to the power of 4. Okay? Communicating levels of a substance like a pollutant in very dilute aqueous solution is often where it is used. Okay, and it's usually used by agencies that set health and safety standards. We also see this on water, right? Generally, say sodium, so many parts per million of sodium within our drinking water. Finally, we have molar concentration. Its symbol is a large capital C. And the formula is the moles of solute divided by a liter of solution. So this is used in communicating the amount of moles of a pure substance dissolved in a total volume of solution. This is used by scientists and lab technicians, okay? So this is one that you would not normally see. Percent by volume and parts per million, you commonly see those in your household products. So in this lesson, we're going to explore how to use and when to use these forms of communicating concentrations. By understanding how concentration is communicated, you're better going to be able to understand the labels of some of your consumer goods that you purchase. You should also be able to make the connections to environmental and scientific issues currently being debated. So, percent by volume. Percent by volume is commonly used for liquids for liquids dissolved in liquids. This form of concentration is usually used for consumer products like drinks and cleaners. The equation for calculating percent by volume is as follows. Okay, so percent by volume concentration of the solution equals the volume of the solute dissolved in the solution over the total volume of the solution times by 100. Okay, so let's do an example problem, and I'm going to show you not only how to do these, but also what the expectation is for you guys to be doing these in the lab, or sorry, in your tests. Many of you also have already seen this. For those of you who haven't, we're going to go through it together. Okay, so a hair product requires you to combine 20 milliliters of hydrogen peroxide with enough water to produce a solution with a total volume of 120 milliliters. We need to determine the percent by volume of this concentrated solution. So first I'm going to write down what I know. Okay, and what I know here is I know the volume of my solute. Okay, this is 20.0 milliliters. I also know my volume of solution. It tells me here with a total volume of, in this case, 120 milliliters. All right, what I don't know, or what I am trying to find out, is my percent volume. Okay, that is what I don't know. So I'm going to use my formula, in this case is percent by volume, okay, equals volume of solute over the total volume of my solution times by 100. Okay, so this goes 20.0 milliliters divided by 120 milliliters. Okay, my units cancel out. I put 20.0 divided by 120 in my calculator. All right, and I should get, and I'm going to take that number, I'm going to times it by 100 because I'm going from a decimal, which I'll get out of here, and I need a percentage, so that's why I times it by 100, okay? And I should get 16.7%. Okay, and here we go. The percentage by volume concentration of the solution is 16.7%. Note, the rules for significant digits state that the final answer must be expressed to the same number of significant digits as the value with the least number of significant digits. So because the volume of the solute consists only of 3 significant digits, the final answer must consist of only 3 significant digits. If you're confused about that, please refer to your calculations with significant digits on pages 534 to 536. It's very important that you understand this. This is one of the outcomes, actually, of Science 20, is that you are reporting your information with proper significant figures, okay? So when problem solving throughout this course, there are key points that you will want to remember. Point 1, mathematical solutions begin by listing the known and unknown values for this problem. That is very, very important. Okay? Secondly, the list of knowns and unknowns is used to choose a proper equation. So we need to list these, and that's what helps us decide what a proper equation is. Third, the data, including units, is substituted into the equation. Okay? The final answer is expressed with the correct number of significant figures with the proper units. Sometimes solving problems requires using algebra in order to rearrange our equations, okay? And I use this basic format in order to give you guys your marks, right? If we all remember, if you guys had me last year, we know that we have to list our knowns, unknowns, formula, substitution, answer, and then there's always this mysterious part here, which is usually a calculation or rearrangement, that sort of thing. But this is for 1, 2, 3, 4, 5, and 6 marks, right? And you guys should know that every written or calculation question for me is out of 6 marks. So let's look at a different example problem here. It says a mosquito repellent says the DEET makes up 45% of the total volume. If you have a 75 milliliter sample of this repellent, determine the volume of DEET within this sample. First, I'm going to list the knowns and unknowns. Well, I know my percent by volume, okay, at 45%. Okay, and I also know the volume of the solution, which is 75 milliliters, and then the question is asking me to determine the volume of DEET within the sample. That's my unknown. That's why I put this lovely question mark there, okay? So next, we need to rearrange the percent by volume equation so that the volume of solute is isolated, because that's what we need to find. Here I'm going to do, I know percent by volume is the volume of solute over the volume of solution multiplied by 100. Okay, so first step, I'm going to divide both sides by 100. That's going to allow me to cancel that out, so I know here I need to divide by 100. Okay, so now I have percent by volume, or V over V, divided by 100 is going to give me the volume of solute over my volume of solution. I am trying to find out my volume of solute. This is what I am trying to isolate. So because this is divided by, I need to multiply this by volume of solution. Cancels those out, and I need to multiply by my volume of solution. Meaning, finally I get percent by volume divided by 100 multiplied by the volume of my solution is going to give me my volume of solute. Okay, then we need to substitute the values into the equation. So the percent by volume that I have is 45%. I'm going to divide that by 100%. And then I am going to times that by 75 milliliters, which is the total volume that I have of this solution. And this becomes 33.75 milliliters as the percentages cancel out. All right, so if we look back here, oh, let me put that down here, okay. If we look back here, and I look at my knowns and unknowns, this has 75 milliliters, which has two significant figures. That is very important because as I come over here, I need to now report my answer in two significant figures, which in this case is going to be 34 milliliters. Checking my answer. So the repellent sample contains 34 milliliters of DEET. Okay? Now, it is not necessary to show all of the algebra in your solutions. Most students simply write the basic equation and then rewrite the rearranged version of the next line. So as you see here, they have the original formula, and then they would just write the rearranged one. If you're able to do that, great. If you're struggling with rearranging equations, then we need to have a talk to make sure that you can get there, okay? The important thing is to remember that the second equation is simply a rearranged version of the basic equation. It is not a new equation, okay? So here we go, yet another one. An insecticidal soap is an environmentally friendly way to control insects and pests on plants. A gardener needs a solution with a percent by volume concentration of the insecticide soap of 5.0%. If the total volume of the solution was 4,000 milliliters, calculate the volume of insecticidal soap needed to create this solution. So, I know my percent by volume needs to be 5%. I know my volume of solution is 4,000 milliliters. And my volume of solute is what I'm trying to find out. Okay, and it says right there, calculate the volume of insecticidal soap needed to make the solution. And the insecticidal soap is the solute in this case. Alright, so I know my percent by volume is equal to the volume of solute over the volume of solution multiplied by 100%. Okay, so if I rearrange this, I'm going to divide by 100. Let's do that in a different color here. So I'm going to divide by 100%, okay, to cancel that out. And I need the volume of solute, so I need to times by my volume of solution. Again, now giving me the same equation as I had before, where I've got percent by volume divided by 100%, cancel out the percents here, times the volume of my solution is going to give me the volume of the solute. In this case is my insecticidal soap. So I am going to take now and sub in my values, so this becomes 5.0% divided by 100%, times that by 4,000 milliliters will tell me the volume of my solute. Okay, and if I put this into my calculator, I take 5, I divide it by 100, I get 0.05, and I times that by 4,000, I'm going to get 200 milliliters. Now, here's where the problem comes. If I look here for significant figures, I've got 2. My answer has come in 3. So I need to report this using scientific notation, so this now becomes 2.0 times 10 to the power of 2 milliliters. And that means the same thing as 200 milliliters. Okay, and if I look here for my answer, right there it says, unfortunately it's hard to see. I'll give this a little erase here. Alright. It says to make this solution 2 times 10 to the positive 2 milliliters of insecticidal soap is needed. Now you need to note that because the percent by volume has at least 2 significant digits, the final answer must be expressed with only 2 significant digits. So to do this, in this case, scientific notation is what is required. All right. Here's a little fun fact. If you combine 50 milliliters of ethanol with 50 milliliters of water, you get a solution with only a volume of 95 milliliters. But how can this be? It is because the molecules of ethanol and the molecules of water do not directly stack on top of each other. Instead, the two liquids intermingle with each other and thus fill in some of the spaces between each other's molecules. This causes them to occupy less volume. And for this reason, if you're making a solution, a specific concentration, you first need to measure the volume of your liquid solute, and then you need to add a sufficient amount of solvent to produce a final total volume of your solution. All right, parts per million. Parts per million is a unit of concentration used for very dilute solutions. You will often come across this unit when you are investigating solutions involving very small amounts of substances in contaminated water, systems, or food. The table, Allowable Toxic Levels in Drinking Water, lists the current guidelines established by Canada Health and Safety for some toxic elements in your drinking water. So allowable toxic levels for drinking water, we've got arsenic. The maximum acceptable concentration is 0.025 parts per million, all right? Fluoride, which is something that we do a fluoride wash for teeth and is commonly used in a lot of toothpastes, is actually only 1.5 parts per million. Other than that, it actually does damage to your teeth, as interesting as that is. All right, so the term 1 part per million means 1 part solute for every million parts solution. The details of this equation are used to calculate parts per million are as follows. So parts per million is the concentration of the solution, all right? And this is the mass of solute divided by the mass of solution times 10 to the power of 6 as parts per million. We need to remember, it's very important here, that 1 milliliter of water has a mass of 1 gram. All right? Super, super important to remember. 1 for 1 in this case. So we have an example problem here. It says a 200-gram sample of a bottle of water contains 5.4 times 10 to the negative 3 grams of mercury. We need to calculate the concentration of mercury in this sample in parts per million. Then we need to use the information in the allowable toxic levels of drinking water to determine if the water is safe to drink. So, what do we know? We know the mass of my solute, in this case, is 5.4 times 10 to the negative 3 grams. For those of us who do not like scientific notation, we're going to convert that quite quickly. All we do is, because this is a negative value, we're going to move the decimal in this direction 3 times. So 1, 2, 3, meaning I now have 0.0054 grams. Okay? My next value here, oh, sorry, I should put here that this is the mass of the solute. Okay. My mass of solution is 200 grams. And the question is asking for parts per million. All right. So here I'm going to take my formula. Okay, my formula is parts per million is equal to the mass of my solute divided by the mass of my solution times 10 to the 6. Okay, so this becomes 0.0054 grams divided by 200 grams. Okay, these cancel out. And then we're going to times 10 to the 6. And this actually equals 27 parts per million. Now, if we go back to our chart here, mercury is quite a bit lower than that for parts per million in acceptable concentration. So, here's a quick calculator tip for you guys using your calculators out there. Calculator tip. So you will be required to perform calculations that involve entering values in scientific notation into your calculator. For most calculators, this requires using a special key labeled EXP or EE. Pressing these keys includes the times 10 part of the scientific notation, so you only need to enter in the exponent. Okay, so this just shows you your keystrokes on the calculator. And what they would mean. All right, so for those of you with that, I can also show you and let you know how to do that. Here we go. If I go back here just to show you guys, so part A here, we did that calculation correctly, and then it says here we know the concentration, okay, in the water is well above the maximum acceptable concentration of 0.001 parts per million, so this water is not safe to drink. Alright, carbon monoxide is a deadly gas that takes the place of oxygen molecules that bind to hemoglobin in our blood. If you are smoking, the concentration of carbon monoxide that reaches your lungs is approximately 200 parts per million. Determine the mass of carbon monoxide that would be present in a sample of air having a mass of 9.6 grams, approximately 1 breath. So express your answer in scientific notation. So, what do I know? I know my parts per million. I know that that's 200 parts per million. I know the mass of my solution, which is 9.6 grams. I know my mass of solute, or sorry, I don't know that. That is my unknown. That's what I'm trying to find out here in this case. Here we go. I'm going to now use my formula. So I know parts per million is the mass of my solute over the mass of my solution times 10 to the 6. All right. Parts per million, sorry. I need to do a simple rearrangement because I need to know the mass of my solute. This is my unknown. That's what I need to find out. Okay. So this now becomes the mass of my solute. Okay, because I'm going to divide this by times 10 to the 6 parts per million. I'm going to divide this by times 10 to the positive 6 parts per million. Okay, and I know that I have to times this now by mass of my solution. Okay, leaving me with the mass of my solute is equal to the parts per million that I have divided by 10 to the 6, or a million, and I'm going to times that by the mass of my solution. So this becomes 200 parts per million. Actually, I'm going to write this up over here. Sorry, guys. Okay. So this becomes 200 parts per million divided by 1 million. Okay, and that's equal to 10 times 10 to the positive 6, sorry. And then I'm going to times that by 9.6 grams. Parts per million is going to cancel out. And this leaves me with 0.0019 grams. Okay, or because I need only 2 significant digits, 1.9 times 10 to the negative 3 grams. All right. So Our answer here is there would be 1.9 times 10 to the negative 3 grams of carbon monoxide present. So now, let's note in this example that the answer displayed on our calculator is not in scientific notation. So to write the answer, we need to follow these 3 steps. First, we need to move move the decimal to the right until it is on the right side of the first non-zero digit. Then we need to round the number to the specific number of significant digits. In this case, we need to round the value to 2 significant digits. Step 3, we need to insert the power of 10, and the value should be multiplied by. Because the decimal is moved 3 places to the right, the exponent is the power, of the power of 10 is negative 3. If you have any questions with that, please ask me. Now, alternatively, many calculators can be set to automatically display the answers in scientific notation. This is a very useful feature because it reduces errors. On many calculators, using the mode key automatically causes answers to be displayed in scientific notation. But check your user guides that came with your calculator to learn how you need to do this. So a little, did you know if you put 4 drops of ink into a rain barrel that holds 210 liters of water, the concentration of the ink would be approximately 1 part per million. So that's pretty insane to think about only 4 drops of ink in a 210 liters of water. But that alone could kill you if it is a toxic chemical. All right, so molar concentration. Earlier in this chapter, we saw how diagrams of atomic structure of a water molecule can communicate that 2 hydrogen atoms are covalently bonded to 1 oxygen atom. Now, if we were to break up this molecule, you would expect to get twice as many molecules of hydrogen gas as you would oxygen gas. Now, the difficulty is that any sample of water contains so many atoms of hydrogen and oxygen that it is impossible to count them individually. Technologists and scientists who need to know the amount of a substance have solved this problem by counting particles in a very large group called a mole. So a mole is a specific amount of substance that consists of 6.022 times 10 to the power of 23, so this should be the power of 23 particles. All right? Molar concentration or molarity is the amount of solute in moles per liter of solution. Now, a mole is a very useful quantity because it enables technologists to combine the precise measurement and precise amounts of substances so that all of the reactants are completely converted into products in a chemical reaction. Since many reactions occur in solutions, the concentration within a specific community are most often communicated in the scientific community are most often communicated using molar concentrations or molarity. The molar concentration of a solution can be calculated using the following relationship. So we have a concentration of solution, so C, and the number of moles in a solution, or N, and then, here we go, and then all over the total volume of the solution, or V. So C equals N over V. Now, this technique is very useful because it communicates the number of molecules or ions of a solution dissolved or disassociated in a specific volume of of a solution. So, a sample of water is taken from a nearby lake and is found to have 0.035 moles of salt in 100 milliliters of solution. Determine the concentration of the salt in the lake. Well, what do I know? I know the number of moles of salt, okay, or of my solute, and in this case it is 0.0035 moles. I know my volume. My volume is 100 milliliters. Okay, but we need it in liters. And I know that for every 1 liter, there is 1,000 milliliters. Milliliters? All right. So this becomes 0.100 liters. Now, that is the reason why we do this conversion is because it's always in moles per liter. That's what concentration is, and that's what we're trying to find out. So I know concentration is N over V, okay? And this becomes 0.0035 moles all over 0.100 liters. Put that in my calculator and I get 0.035 moles per liter, or 0.035 molar. Now because I have two significant figures right here, I know that this now needs to be reported in two significant figures. Those are my two significant figures. It is 3.5 times 10 to the negative 2 moles per liter, because I've had to make this movement here and move my decimal into that spot. Okay, so there's my movement. Now, here we go. The concentration of the salt in the lake is 3.5 times 10 to the negative 2 moles per liter. Throughout this course, when you record your measurements or do calculations, you should always include the units. It's very, very important. In the example that we've already done, the volume of the solution was given in milliliters instead of liters, and it is essential to communicate in a clear and concise way how to convert one unit into another. So one of the best ways of doing this is using a conversion factor. A conversion factor is a fraction used to convert one set of units into another. The conversion factors offer a concise and consistent way to sort out your units. And these conversion factors not only keep your solutions organized, but they help to keep you thinking clear by giving you a reliable way to handle units in all solutions. So if you want more information about that, it's on page 532. Now, molar mass. So sometimes it is necessary to first calculate the number of moles using the mass of a sample and information from the periodic table in order to determine molar mass. The equation for calculating the number of moles in a substance is as follows. So molar mass is the mass of 1 mole of a substance, and we use N to represent the number of moles, okay? Lowercase m to represent the mass of the substance, and then the large M to represent the molar mass of the substance. So is N equals M over M, with lowercase meaning grams. So example problem. You dissolve 30 grams of sodium sulfate, Na2SO4, into 300 milliliters of water. We need to determine the number of moles of sodium sulfate in the solution, and then we need to calculate the molar concentration of the sodium sulfite solution. So first we need to determine the molar mass, or M, of Na2SO4. That is the very first thing that we need to do. And when we look at this, we notice we've got some subscripts here. These indicate the number of those atoms within that compound, okay? So I've got 2 of my mass, or my molar mass, of sodium, plus just 1, because I don't have a subscript here for my sulfur, so only 1 mass of sulfur. And I need to add 4 the mass of oxygen. Sorry, I ran out of room there. Alright, so this becomes 2 times 22.99 grams per mole. And I find that value here. It's in a different spot in the periodic table that we're using. So just to keep that one in mind, okay? Now I'm going to add 32.06 grams per mole for the sulfur, and I'm going to add 4 times the amount of the molar mass of oxygen, which in this case is 16.00 grams per mole. And I'm going to get a total amount of 142.04 grams per mole. Alright, so that's the molar mass of that particular substance. Now, we need to calculate the number of moles. So, the mass of the solute that I had was 30 grams. The molar mass of that molecule is 142.04 grams. And I need the number of moles. I need that N. Okay? The equation for molar mass is N equals M over M. And I'm now going to do that substitution of 30.0 grams divided by 142.04 grams per mole. All right? And that gives me 0.211, and it just keeps going. 3 significant figures, 5 significant figures means that I report it in 3 significant figures. So 0.211 moles. Okay, so the solution contains 0.211 moles of sodium sulfate. Next, we need to look at the molar mass. Next we need to calculate the concentration. Okay, now I'm going to use the number of moles that I had in my calculator. So there's a good reason why we wrote all those numbers down. Okay, this is what I know. I also know the volume is 300 milliliters. I use my conversion factor, knowing that 1 liter is 1,000 milliliters, and I get 0.3 liters. And then my concentration is what I'm trying to find out. So note that although the number of moles was rounded to 3 significant digits in part A, you should use the unrounded value in this calculation to get a more accurate answer to part B. Remember, the number of moles is still considered to have 3 significant digits in the calculation. So concentration is number of moles over volume. So this becomes 0.211281104 moles all over 0.300 liters, which gives me a concentration of 0.704 moles per liter. All right, that's right. Oh. Right there, the molar concentration of the sodium sulfate solution is 0.704 moles per liter. There you go. There's a whole bunch of lovely science for you to bombard your mind, and we'll have lots of time in order to practice this in class and make sure you understand these concepts. Be sure to write down any questions and things that you would like me to cover. Thanks so much for watching, and have a great one.